Okay, so it's our great pleasure to have Professor Krishna Balasubramanian as our webinar speaker today. Krishna is an associate professor in the Department of Statistics at UC Davis. He also holds affiliation with graduate group in Applied Mathematics, the Center for Data Science and Artificial Intelligence Research, and the Tetrapods Institute of Data Science. Krishna's research interests are centered around the intersection of machine learning, optimization, and statistics. His research has been supported by a Facebook PhD fellowship as well as grants from the Center for Data Science and Artificial Intelligence Research and the National Science Foundation. Krishna serves as associate editor for the Journal of Machine Learning Research and as senior area chair for a lot of conferences such as ICML, NeuralNIPS, and the Conference on Learning Theory. And today he's going to tell us optimization-based analysis of sampling algorithms. Welcome, Krishna.
Okay, yeah, thanks, Jiva, for the kind introduction, also for inviting me to present in this webinar series. So because I'm not really sure like what's the how diverse the background of the students and the faculty and industrial affiliates are in this meeting, so I'll keep it at a high level. And if there's any technical questions, I'll be happy to deal with it. You can just interrupt me in the middle of the talk or ask me about it in the end of the talk, right? All right, so let's start with the following problem setup. So the goal of this talk, and more broadly, the goal of this line of work that I've been working on recently, is to understand and develop a complexity theory of sampling, in particular when you're dealing with targets that are non-log-concave, right? And so I'll keep track of the questions, or so this is some channel. Okay, good. Yeah, so for more statistical audience here, why do we have to care about this problem? So we know that in Bayesian inference, you always have to sample from the posterior density. So that's very important, and it's kind of like the computational foundation of like the Bayesian inference in some sense. But more broadly in applied mathematics, you'll also deal with like numerical integration problems where you will end up sampling from a particular target distribution, right? And also in machine learning recently, approaches for differential privacy has been based on like sampling algorithms. And unless you have been living under the rock, you should be aware of like ChatGPT and diffusion models and all this related generative AI techniques, where the underlying thing is essentially sampling from a distribution or density which is not given to you in closed form, but you have samples from that and you want more samples from that. So in some sense, this problem of sampling from a particular target density has wide applications. Our goal in this talk will be, the focus will mainly be on the non-log-concave setting, right? So let's gradually build towards what do I mean by non-log-concave setting here. So let's say our density is given to us in terms of this parameterization. So let's say you have pi to be exponential of some minus v, and v is typically called as the potential function. And if v is convex, for example, something like this, sort of a lot of things are understood about sampling in this setup. But then like gradually as you move towards the right, the density or the potential becomes non-convex, more and more non-convex, so to speak. And correspondingly, the density will become more and more log-concave, right? I mean, non-log-concave, right? So if the potential is convex, the density will always be log-concave. So now, this is obviously the absolute value function, and here in the dotted red line there's a quadratic function, so which corresponds to the Gaussian density, right? So we also have some notions of like functional inequalities, which will become clearer a little bit more in the later part of this talk. You say that a density satisfies this particular inequality, either Log-Sobolev or Poincare inequalities, if it's essentially sort of like some minor perturbations of the quadratic density case, roughly speaking, right? So you have the Gaussian, which is the red curve, and then like you have some non-concave perturbations. So the overall blue curve here is non-concave, but it's not too non-concave. It's sort of closely following this quadratic function. Similarly here, it's closely following the absolute value function, but it is still non-log-concave, or the potential V is non-convex, right? And these are sort of like intermediate non-log-concave densities or non-convex potentials V. But what do I mean by a truly non-log-concave density or a truly non-convex potential is like when you can have mixture of Gaussians or arbitrary multimodal densities in some sense, right? So this will be our focus for this talk and for this line of work. And I also want to point out that heavy tail densities, which also have wide applications in various fields, also are covered or something that is of interest and falls under our setup. And in particular here, notice that if you have this, if you look at again this red line for reference, that's the Gaussian we all are familiar with. The potential here is just flat. So if you draw a quadratic function here, it will be like growing to infinity much faster, whereas this is not at all growing. It's almost like tapering off in some sense, and it's like flat. So if you do the e to the minus v for this v, you will have what are called as like heavy tail densities, and these are also like non-log-concave. So some sort of like non-convex potentials. So lead to non-log-concave densities at the end of the day, right? And the viewpoint that will be taken in this line of work is based on the seminal paper by Jordan, Kindle-Lehrer, and Otto, which proposes to view the sampling problem as essentially optimization on the space of densities, right? So we know, we sort of have classical optimization problem. So if you're a frequentist statistician, you basically have some maximum likelihood. So you are maximizing something or minimizing something, which means that's an optimization problem. Except that there you have typically a parametric model, and the parameter is in terms of like a d-dimensional vector. So that MLE, for example, would be an optimization problem on the Euclidean space. So with respect to the Euclidean geometry and everything. So here, in the case of sampling, what this paper proposes to view as is like, it's essentially the same optimization problem, except that you're doing your optimization on the space of densities directly. So you're keeping track of densities and its evolution, right? So this viewpoint has actually inspired a lot of researchers recently to develop novel theory for sampling algorithms based on essentially optimization tools, right? And for a very interesting and comprehensive survey up until 2002, I would refer to this tutorial by Korba and Salim in ICML last year, right? And so when you're optimizing something, we need to have an objective function, right? So we need to have an objective function with which we can optimize, right? So what is the objective function here? So the objective function here is given by the KL divergence, right? So given any two densities, nu and pi, the KL divergence is given by this expression here. And the geometry is something which we need to define gradients and derivatives and things like that. So that is taken to be as something called as the Wasserstein 2 geometry. So if you're aware of it, it's good. If not, you can just think of it as like the natural analog of sort of the Euclidean geometry in the space of densities, let's say. And what is now the sampling problem? Sampling is essentially just optimization where you're minimizing the scale divergence over the space of densities with respect to this geometry, which is what I have denoted here by this red W2 of RD, right? So this W2 of RD consists of all the space of densities on RD, and given an initial density mu naught, you want to take that mu naught in this geometry to your target pi. So pi will always denote our target, right? And that is exactly how one should think of, I mean, this paper proposes to think of optimization, sampling essentially as optimization on the space of densities, right? And based on this, we have something which is a natural analog of gradient descent. For example, if you're having a Euclidean optimization problem, the first algorithm one could think of is like gradient descent. So you take the negative gradient and then go in the direction of that, right? And if you do the continuous version of it, you have something called as the Euclidean gradient flow. And the natural equivalent or analog of Euclidean, the gradient descent for solving this optimization problem in the continuous time is what is called as this Wasserstein gradient flow, right? So here, what is this mu t? So this mu t itself is a density function, right? So it's an infinite dimensional density function, right? And this thing in blue, which is the grad log of mu t over pi. So this is what is called as the Wasserstein gradient, right? So in Euclidean gradient descent, you basically take the gradient of an objective function. This is exactly what is called as, it's the exact analog of gradient descent, except that now your gradients are functionals themselves, right? So you have something called as the Wasserstein gradient here. And this equation in some sense corresponds to something called as a gradient flow. And you can discretize it and things like that to do some actual algorithm in practice, right? So now, so this is exactly what I told. So this term is what is called as the Wasserstein gradient of the KL evaluated at the mu t point, right? So let's come back to this later, but I want to connect this more to a very statistical classical perspective. So suppose that we do not know this sort of a viewpoint, as sampling is essentially optimization on the space of densities, right? So suppose that we do not know that. And what has been classically thought of, like much before 1998, for example, around 1950s, people were looking at Markov chains and Markov chain Monte Carlo algorithms, right? So that has been the driving force in some sense of classical sampling algorithms. And the idea there is totally different, at least at a very high level, they appear to be seemingly very different, right? So how would you sample from a given target density pi? So you set up some Markov chain whose stationary distribution is the target pi. That's exactly how we would start with. And a classical example is what is called as this Langevin diffusion. So where you have this equation, one can show that. So recall that this V is exactly the potential function. So V is essentially this e to the minus V. So you can write this equation down given a target. And under assumptions and conditions, one knows that the stationary distribution of this YT of this Markov chain will essentially be your target, right? And then now you have this continuous time analog, and then you can basically discretize it and get an actual algorithm, and that is classical MCMC technique, right? So here comes the equivalence. So this classical perspective here actually is tied to what I introduced previously, right? So recall what is mu t. Mu t is essentially the Wasserstein gradient flow, the evolution of the gradient flow, where this mu t is a density itself, right? And what is this yt in a Markov chain? That is actually the random variable, or it's sort of like a stochastic process, or for every t, it's sort of like a random vector, let's say, right? So it turns out that these two perspectives are equivalent in some sense, because here we are talking in terms of the random variable. Here we are just talking in terms of the density of that random variable. That's it, right? So essentially the law or the density of this random variable is just exactly given by this equation mu t here, right? And that is exactly what I've written down here. So the Wasserstein gradient flow sort of tracks the evolution of the density of the Langevin diffusion. And that is literally the idea proposed in this paper, or the connection which was observed in this paper by Jordan, Kindle-Herrera, and Otto, right? So this also suggests that this Markov chain perspective also has an underlying optimization problem behind the screens, right? So Let me pause here for a minute and check to see if there's any questions before we proceed. All right, so if there's no questions, let's proceed. So now you have sort of at least two perspectives in hand, which turns out to be they are both equivalent. So you can either track, so the T here in either this Langevin diffusion or the Wasserstein gradient flow, the T here is all continuous time parameters. So you cannot implement this algorithm in practice on a computer because you cannot obviously implement continuous time things in a computer, right? But now to implement these things in a computer, you have to discretize either this equation or discretize this equation, right? So that's how actual practical sampling algorithms are constructed, right? So you basically have sort of like multiple ways of doing things, or actually constructing sampling algorithms. So the first way is you take your diffusion, Langevin diffusion that I introduced, and then you discretize it. And that gives rise to some Markov chain Monte Carlo algorithms, which are classically studied in statistics, right? And you can also take this Wasserstein gradient flow and then discretize it directly on the density space. And that gives rise to what are called as particle-based sampling algorithms. And there is also another sort of third class of algorithms, which are called as variational inference algorithms. So here you're optimizing, instead of optimizing over the set of all densities, you'll be optimizing over a specific subset of densities, which are more tractable in practice. So let me explain each of these things with an example. So in this algorithm, your n is a discrete time step. So you can basically implement this in a computer. And what is this algorithm? This algorithm is exactly a discretization of this continuous time diffusion process, right? And this algorithm is exactly what is called as the Langevin Monte Carlo or unadjusted Langevin algorithm, right? And here un is a standard normal vectors, right? And because you have some BT, which is a Brownian motion, you sort of discretize it through the standard normal vectors here, right? And more popular and other discretizations include the metropolis adjusted Langevin Monte Carlo and the proximal Langevin Monte Carlo, and so on and so forth. And then there's Hamiltonian Monte Carlo, and all these algorithms are there, right? So this is one class of algorithms. The thing I want to point out here, which I have it in red here, is this UN. This is something that you are actually adding in the algorithm, right? So suppose you just look at this algorithm as such. This V is something that is given to us because we know what is the target density. So V is the potential of the target, and we know exactly what it is. But this U is something that you are using in the algorithm. So it's some artificially injected noise in the algorithm in some sense. So which is why MCMC algorithms are randomized algorithms in some sense. So there is some inherent randomness in the algorithm, right? So the second example is based on a different approach, and it is called as the Stein Variational Gradient Descent. And the meaning behind this algorithm is you have this Wasserstein gradient flow here. So this mu t is actually a density, right? So densities are infinite dimensional things. So you cannot actually implement it on a computer. So you need sort of particles, which are, you can think of particles as n samples from the densities, right? So you have n samples corresponding to these densities. And then this t is also a time index. So the t is also a continuous time index. So you also have to discretize this time index, right? So this sort of corresponds to space-time discretization of this Wasserstein gradient flow, or some approximate Wasserstein gradient flow. So in order to do that, you take a bivariate kernel function, like just some RKHS kernel or something like that, and you exactly do this updates. So in each iteration, you compute this you first compute this and then you update your xi's from your previous step using this new step here, right? And what do you need to know to implement this algorithm? So firstly, the user has to pick the number of samples that you need to approximate the density. So remember, density is infinite dimensional object. So you need n samples to approximate it. That is user specified. And this h is some tuning, the step size parameter that you need to have as a supply to the algorithm as a user. And kernel is something that you need to pick, but the v is given to you. That is the target density, right? So the main thing, it's not very important to understand the exact expressions here, but the main thing I want you to focus on is both algorithms are based on the gradient of v. So you are evaluating the gradient of v in both the algorithms, right? But in this algorithm, there is no additional artificial injected noise. So whereas in this algorithm, there is actually a Gaussian vector which you're injecting in each step, right? So while MCMC algorithms are randomized algorithms for this reason, SVGD is actually a deterministic algorithm for sampling because there is no artificially injected noise. So for example, you run this algorithm from a starting point, say you do that for 100 times. Let's say you run it for 100 iterations each time. The output of the algorithm will be different in each of the 100 trials, although you run it from the same starting point, because in each iteration you are injecting noise here. Whereas for this algorithm, you start from the same point, you repeat it 100 times, you will exactly end up at the same point each of the times, like each of the 100 times. So this is a deterministic algorithm. So there's no need to quantify the fluctuations and so on and so forth here. So that's a benefit in some sense of deterministic algorithms in some sense, right? And there's this third class of algorithms which are called as this Gaussian variational inference algorithms. So here, so recall here that your optimization viewpoint, in this optimization viewpoint, you're trying to optimize over the class of all densities here. Whereas in variational inference, what you do is you try to find, especially in Gaussian variational inference, you try to find the best Gaussian, which is an approximation to a given target density. So your target density could be anything, but you want to find the best Gaussian approximation to it, right? And how do we define the best? It's in terms of like minimum KL distance, a KL divergence, right? So the advantage is that here, because you don't have a parametric form for the density in SVGD, you have to use n particles to track the density in some sense. In the Gaussian variational inference, because your output is Gaussian, all you need to know to track a Gaussian density is just the mean vector in the covariance matrix. So it's enough to just track a vector and a matrix. So that's the nice thing, some nice thing about this Gaussian variational inference, right? And so it turns out, I will explain this more in the later part of the talk, but it turns out that you can actually have deterministic and stochastic versions of these algorithms, but they are not truly randomized algorithms because you will not be actually injecting any artificial noise here. So they are, you can think of them as some sort of semi-randomized algorithms, right? All right, so now we have introduced this framework and different types of algorithms. So now let's talk about some guarantees for these algorithms and how do we evaluate these algorithms in some sense, right? So in particular, if V is convex, your objective function also turns out to be convex. So there's a lot of work in this case for each of this Langevin Monte Carlo, SVGD, and GVI, including some all of these are very recent works. But our focus, as I told in the beginning of the talk, is considering the case when V is non-convex, where much less is known, right? And okay, so now that we have looked at, all the while we have been motivating this sampling problem as sort of like an analog to optimization, right? So let's ask ourselves, okay, so in optimization, in particular non-convex optimization, how do people develop guarantees for some gradient descent or some classical algorithms for non-convex optimization, right? So obviously, in general, for arbitrary non-convex functions, you cannot have any sort of global convergence guarantees, right? So because the function can be arbitrary non-convex, it might take exponentially long time to get to the global minima. But what we can do is ask ourselves, are we converging to a reasonable stationary point, right? And in particular, we can think of first order stationary solutions where the gradient is zero. At least you have the gradient is zero at the point where you converge, right? So it can either be a local min or a local max or a saddle point, but at least you know the gradient is zero at that point, right? And people have looked at this very carefully, and in the Euclidean optimization, so if in order to get a point x such that the gradient is of this order, you need to run the algorithm for 1 over epsilon time steps, right? So now we have to ask ourselves, okay, so what's the natural analog of this sort of a convergence guarantee in sampling, right? So it turns out your objective is the KL divergence. So the gradient of this objective is exactly this grad log mu over pi. So you can just define, and this is exactly what is called as the Fisher information between mu t and pi. So the expected, this quantity here is exactly the analog of the first order stationary solution for sampling or non-log-concave sampling. So your question is going to be, how many iterations should I run the algorithm for so that the Fisher information between the tth step and the target distribution is less than epsilon, or up to some tolerance that you wish to allow in your algorithm, right? So that will be our goal. Or that will be the notion of first order stationary solution for sampling, or that we are proposing in this line of work, right? Okay, so now let's understand this stationary notion of stationarity a little bit more. Say you're given two mixture of Gaussian distributions. So you have mu to be, you have pi to be a mixture of normal, which is this 50-50 label proportion. So each of it has mean minus m and m. In this example, it's -2 and 2. And 50-50 is the blue curve, and 3/4, 1/4 is the orange curve, right? So, and m is something which is larger than 0, obviously. So it turns out that if you have two densities like that, for any m, which is like sufficiently large, the total variation is always lower bounded by an absolute constant, independent of m here, right? Whereas the Fisher information actually goes to 0 when m goes to infinity, right? So what this is telling is that the Fisher so obviously these two densities are not the same densities, right? So Fisher information going to 0 is exactly like a weaker sort of a condition than total variation. So for example, if Fisher information can go to 0, but total variation may actually not even go to 0. It will be bounded below by an absolute constant, right? So in this example, as we illustrate here in this example, right? So it's exactly as in the optimization world, right? So if you're converging to a point where the gradient is 0, you will still not be able to distinguish between the maxima, whether it's a maxima or a minima or a saddle point. So that is still there, but at least you know that the gradient is 0 at that point, right? And why should we care about that? Actually, it turns out that Fisher information for a sampling problem captures some sort of local mixing of your diffusion or your process in terms of the modes of the distribution. And a lot of complexity in terms of like the sampling, especially in the multimodal non-log-concave case, arises because of having to jump with one mode to another mode. So that's exactly the main issue, and that is called as metastability in sort of physics literature. So this notion of Fisher information is actually converging how quickly you will converge to a mode, not all the modes even, but at least a mode. So it's exactly like a local convergence guarantee. And in a lot of statistical problem, it turns out that you can have these modes to be actually having very interpretable statistical meaning, right? And that's why we should care about, in some sense, how fast you converge to a Fisher information in terms of Fisher information for a sampling algorithm. right? And there's also very nice recent works building on our works by Cheng et al. On this notion of conditional mixing in MCMC. Instead of global mixing, it's actually conditional mixing, meaning that mode convergences in some sense, not the global convergence in a way, right? All right, so this is sort of like the background that I want to give for the talk. So in the rest of the talk, I will present the guarantees that we have for the 3 algorithms that I introduced. So maybe it's a good time to hold on for a second and see if there's any questions before we move on. All right, so if there's no questions, let's move on. Let's see exactly how many iterations sort of do you need to for this Langevin Monte Carlo algorithm to converge to a first order stationary solution, right? So this section of the talk is sort of based on this paper in arXiv, which is appearing in the COLT conference in 2022, which appeared in 22 COLT. So this is exactly the Langevin Monte Carlo rewritten in a convenient form, which is more interpretable in some sense. So you think of it as like h as some step size parameter, and you're going from iteration k to iteration k plus 1 through this sort of a update step, right? So the question of interest is like the Langevin diffusion rapidly converges to the stationary density. So the diffusion means that always is a continuous time thing, and the Langevin Monte Carlo means that it's the discrete time thing. So firstly, when does this happen, and when does convergence of the diffusion imply convergence of the algorithm, the practical algorithm itself, right? And if you recall from sort of like the beginning of the talk, we introduced something called as like log-Sobolev inequality. The meaning of log-Sobolev inequality is the Fisher information between 2 densities is greater than or equal to the KL divergence. If it holds for every density mu, then we tell that pi satisfies LSI or log-Sobolev, right? And if you recall from the beginning of the talk here, is covers situations where your true density or a target is like non-concave or non-log-concave, but then it is still closely aligned to a quadratic, like Gaussian-like behavior. It has a Gaussian-like behavior, right? So in that case, the optimization analog of this LSI is exactly what is called as this Polyak-Losashevich condition in non-convex optimization. The gradient squared is essentially greater than or equal to the function value. So essentially the gradient squared is greater than the function value is the meaning of this LSI inequality, right? Although the original proposal of this LSI inequalities were totally from a different angle, it has this nice analog in Euclidean optimization as well, right? And there's a line of work, as I told in the last several years, where which analyzed convergence of LMC and the Langevin diffusion under this LSI assumptions, and more generally under Poincare assumptions, and so on and so forth. So however, we want to really go beyond all these specialized cases and look at truly non-log-concave densities. So in particular, the only assumption we make on the density is that it has gradient, the potential V has L-Lipschitz gradients, right? So given any 2 points x1 and x2, the gradient at x1 and the gradient at x2 of V is upper bounded by some L times x minus V. So this is the only assumption. We do not make any restriction on the allowed multimodality, whatever, right? This is really the only assumption that we make. And then this is the guarantee that we have for the algorithm, right? So if you denote by mu t the law of the tth step of your Langevin Monte Carlo, the Fisher information between mu t and pi integrated over this time period is upper bounded by this initial distribution that you supply divided by nh and 8L squared times dh, right? And what is d here? D is the dimensionality of your problem. And what is h? H is the step size that you have to pick for your sampling algorithm, right? And this is the condition that you have on the H. So, and that depends only on knowledge of L. And what is L? L is like the gradient Lipschitz constant of the potential, right? So this is the only condition that, I mean, the only under the assumption that the gradient is V Lipschitz continuous. If you pick your H accordingly, you will have this sort of a local convergence, right? So it turns out that you can if your the initial divergence is upper bounded by some k naught, if you pick your H to be exactly this value, then you have it's basically like you have H in the denominator here, H in the numerator here. You pick H to balance the both, and then you can get a much simpler bound. So the actual bound is not important, but let's look at how to interpret it. So what it says is that suppose that you want to generate a point such that the density at the point is denoted by this mu bar, and pi is your target. And these two densities, in terms of Fisher information, you want that to be some less than epsilon, some given epsilon, right? So then how many iterations should I run the algorithm for? It turns out that you should run the algorithm for L squared D squared over epsilon squared iterations. So, and epsilon is the user specified tolerance parameter, right? So that is exactly how we interpret this result. So you, as a user, you have to give me an tolerance that you allow. So I want to converge locally up to some accuracy 10 to the minus 10, let's say, and that would be the epsilon. And then this would be the overall number of iterations you need to, upper bound on the overall number of iterations that you need to guarantee that you will actually get a point which is epsilon close, right? And this is exactly the guarantee that we wish to have, and we have it now for the Langevin Monte Carlo algorithm here, right? So there are also some other benefits about this optimization-based viewpoint of this Langevin Monte Carlo. So I don't know how many of you have looked at like any MCMC books and looked at the, for example, convergence to stationarity or some weak convergence sort of results for some MCMC algorithms. But if you open any book, invariably you will have a set of conditions, at least half a page or 3/4 of a page. So based on some Lyapunov techniques, and then there'll be like some sort of sets in which it has to do something, and actually all these conditions will sort of boil down to half a page or 3/4 of a page. But actually using this technique, we can immediately guarantee that as long as your LMC, as long as your potential is satisfying only this assumption, there is no Lyapunov type of conditions. As long as you have this type of an assumption, you also guarantee weak convergence if you pick your step size sequence in this order. So you can have some sort of a weak convergence results immediately, right? And yeah, so other approaches, as I told, if you open, for example, any of this Markov chain book, you will find half a page of conditions. We don't need any such condition. That's one advantage of having this optimization viewpoint. All right. So now let's move on to the second algorithm. So the second algorithm is essentially the Langevin. The first algorithm was Langevin Monte Carlo. The second algorithm is something called as SVGD, the Stein Variational Gradient Descent. So recall that the Stein Variational Gradient Descent is actually a deterministic algorithm. So there's no injected noise in the algorithm. This part of the talk, or this section of the talk, is based on this paper in archive here. And it is under minor revision at the Foundations of Computational Math journal, right? All right, so just recall from the beginning of the talk that the Wasserstein gradient flow, which is the density evolution perspective, has this sort of a form. So the form is not important, but it's just like an expression to keep in mind. And SVGD proceeds by obtaining a space-time discretization. And why is it space-time? So the T is a continuous index, and the mu density is actually a density, so it is infinite dimensional. So you need n particles to approximate the density, and then you need some time, discrete time, to approximate the T. So actually it turns out that you cannot approximate the Wasserstein gradient flow exactly for some technical reasons. So people actually have to work in a restricted space And the way to work in this restricted space is through the use of reproducing kernels. So without going into the details, a reproducing kernel is essentially like a symmetric positive definite function taking two arguments and giving out some similarity information. And for just for the sake of simplicity, we denote by this T of k comma mu a mapping from the space hk to this L2 space, right? And what is the space hk? Hk corresponds to like a function space which is characterized by the kernel, and that is called as the reproducing kernel Hilbert space. If you're familiar with it, it's good, but if not, think of it as some subset of L2, right? It's just a restrictive space, right? And with this notation, I'm just going to introduce what is called as this regularized kernelized Wasserstein gradient flow. And if you ignore this thing that I've highlighted here, the remaining thing is exactly the Wasserstein gradient flow. Nothing has changed here. So this is the Wasserstein gradient flow. If you ignore this highlighted thing, that is exactly the Wasserstein gradient flow. Now you have an additional term nu here, which is some constant between 0 and 1. So let's pick nu is equal to 1. So when nu is equal to 1, this term is 0. So you only have identity inverse, which is identity, and you're left with this thing here. So in addition to this Wasserstein gradient flow, you have this term here, right? And that is exactly what I mean by working in a restricted space instead of the Wasserstein gradient flow, right? And the SVGD algorithm turns out that you're doing a space-time discretization of the Wasserstein gradient flow with this additional term included. But recall that we ideally want to work with the Wasserstein gradient flow, which means that you should discretize this. So in order to do that, notice that when nu goes to 0, so this term is gone. So pretend that this is not there. And this term is essentially like just nu is 0, so that is gone. So all you have is this, think of this as a matrix inverse times the matrix. So this whole thing will be gone, and you sort of recover back the Wasserstein gradient flow here, right? So this new parameter sort of interpolates between what is called as this SVGD at one end and the Wasserstein gradient flow at the other end. And we want to be as close to nu equals 0 as possible in some sense, right? And that's when you'll be more general in a way, right? And it turns out that once you have this flow, you can discretize it in both space and time. And the algorithm is a little complicated, but it has some form similar to the SVGD algorithm that I introduced previously. And the point is that all you need to know about the target density is still only the gradient of the V. So as long as you know the gradient of your potential function, you're good. So you can still implement this algorithm, right? And for this algorithm again, so we have this Fisher information guarantee. So under a lot of assumptions, if you pick your new parameter appropriately, and if you pick your step size parameter appropriately, so one can guarantee that the Fisher information is bounded by this term, and the new has to be actually picked so that this goes to 0, so that or essentially this controls the rate of convergence of the algorithm, right? And in addition, so this result is true for any target which is just satisfying this assumption from before, right? Just the gradient Lipschitz condition here, right? But in addition, if you have LSI or log Sobolev on your target, you can get exponential faster rates of convergence, right? So I'm sort of glossing over the details here, but the type of results are very similar to what I introduced for the Langevin Monte Carlo. So essentially, it's still a first order stationarity guarantee, except that the algorithm is now a deterministic algorithm rather than the MCMC type sampling algorithm, right? All right, and in the remaining time I will have left, I'll just briefly touch upon this Gaussian variational inference problem. And this talk is, this work is, I mean, this part of the talk is based on this paper appearing in arXiv here, which is published in ICML 2023. All right, so recall that your sampling problem is essentially optimizing the KL divergence on the set of all densities In Gaussian variational inference, you restrict to a subset, which I've denoted here by BW. So this BW is what is called as the Bures-Wasserstein space. So this is the Wasserstein space, this is the Bures-Wasserstein space. And what is this space? So this is essentially like the subset of all densities which are Gaussian. So this is, instead of optimizing over all densities, you are optimizing over only Gaussians. That's exactly what it means, right? And it turns out that this BW space has a nice Riemannian structure associated with it, because of which you can actually do easy calculations relatively compared to this general space. And another advantage is that because it's Gaussians, you do not have to track it non-parametrically. You only have two parameters, the mean and the covariance matrix. So all you need to do is keep track of the mean and the covariance here, right? All right. So so how do you solve this problem? So that's what we are going to look at next. So to do that, we will again get more insights from what they do in optimization, right? So to see why, first recall that this is the KL divergence, and you can define something called as the entropy as something like this, and the potential energy as just the expectation of this V function. With this notation, actually it turns out that this KL divergence, which is given by this thing here, has this summation of V plus H form. So it turns out that minimizing this objective is actually equivalent to minimizing this V plus H over the same space BW of RD. And why do we have to rewrite it in this particular manner in terms of this V and H? It turns out that one of the functions is like smooth and the other function is convex, meaning it's also non-smooth. It can also be non-smooth, right? And again, in optimization, people have developed the whole machinery to solve optimization problems of this form. So where V is a smooth function and H is a convex but potentially non-smooth function. So in Euclidean optimization, the standard algorithm to solve this problem is what is called as this forward, backward, or proximal gradient descent algorithm. So if you do not have this term here, the remaining things in this equation is exactly gradient descent. But because of this non-smooth term, you have to do something called as this proximal mapping here. And this algorithm is what is called as proximal gradient descent or forward backward algorithm in some sense, right? And now why are we discussing this? Our problem in the sampling case is having a very similar structure here, because this V and H, one of it is smooth and the other one is just convex, non-smooth, right? So you can ask, how do we design this forward backward algorithm? And that is exactly what we ask ourselves next. And it turns out that so this JKO stands for Jordan, Kindle-Lehrer, and Otto. It turns out that this proximal expression here has a nice closed form solution. So the details again are not very important. So you can it turns out that you can implement an algorithm like this for solving this optimization problem on the space of Gaussians, and that would look something like this. So the thing I want you to focus on in this algorithm is look at this little m and this sigma. So little m is the mean, the sigma is the covariance matrix. So this is a vector and this is a matrix. At the end of the day, you will be outputting a normal distribution with that mean and that covariance. So that is your output of the algorithm. And you will be given a target, and that is given to you. And you start with some Gaussian, which is m naught and sigma naught, right? And how do you update from m naught sigma naught to this mn sigma n? So you do this iterative updating scheme. So the mean is updated based on this, and the covariance matrix is updated based on another, like some complicated looking formula. But essentially the bottom line is it's motivated from this computation of this proximal term for this particular problem, right? The point is, the point that I also wish to emphasize here is that if you remember from the beginning of the talk, I mentioned that this Gaussian variational inference is sort of like a semi-randomized algorithm. The meaning is that, or the reason is that So if you are treating this algorithm as a deterministic algorithm, you have to keep track of an integral due to this expectations here. But that is actually the thing that you're trying to avoid in the first place, right? So you actually have to deal with samples here. And so what you do is in each iteration, you draw a particular sample from this Gaussian from your previous step, and then you update the mean and the covariance in the next step. So something like that is what you do. And this leads to stochastic algorithms because this grad v at this x hat k, because x hat k is a random vector, this is a random vector and this is a random matrix. So if you're operating in the practical stochastic setup, this is a random algorithm or stochastic algorithm. But the important thing to note here is I'm not artificially injecting any noise like we do for the MCMC or Langevin Monte Carlo algorithm. So in some sense, it's a semi-randomized algorithm, I would say, right? So, and with this, again, I'm not going to go into the details here, but so the results that we have is like, in order to get an epsilon approximate solution in either the strongly convex or the convex, or more importantly, this non-convex case, by which I mean the Fisher information has to be less than epsilon. So this is the number of iterations that you need to run your algorithm for. So this is for the FBGBI, meaning for this like not practical algorithm. And this is the current result for stochastic algorithm, which is the actual algorithm which we could implement. And in this case, actually the non-convex is open still. So this is essentially, but it could be done actually. It's just not done in this paper, but it could be done, right? All right, so let me summarize my talk so far. I mean, talk today. So what we did in this talk is introduce or propose this notion of local convergence or convergence to stationarity for sampling algorithms. So this is in stark contrast to classical way of thinking about Markov chains, where sort of global guarantees are asked. But then you only get into like exponential bounds or exponential dependencies in dimension and slow runtimes and so on and so forth. But of course, that's bound to happen. So what we do is we relax ourselves a little bit and then ask, so what happens locally, right? So that is the main thing that I want to emphasize here. And it turns out that there you can actually get analogous or meaningful quantities like what we do in optimization. And then I discussed about like complexity guarantees for three algorithms: LMC, SVGD, and FBGBI. I mean GBI, yeah. And for all these algorithms, you can sort of have like local guarantees under the only assumption that your gradient is L-Lipschitz, right? So that's the main key idea here. And if you don't understand anything in this talk, the main take-home message is like you can take any good book on optimization and read that, and I'm 100% or maybe 99% sure that the algorithm or idea in that optimization book could be translated to sampling to get some new insights in sampling as well. So that's the main take-home message I want to deliver in this talk, right? And with this, I will be happy to take more questions. Yeah, thank you.
Thank you so much, Krishna, for the nice talk. Let's move to the Q&A session.
Sure. Yeah.